Hi everyone. In this video I'll be talking about 13.2, 13.5, and 13.6. This is our last material. So let's get into it. We've been talking about exponential functions recently. So what we're going to see here is another technique of how to solve exponential equations. So here's a reminder of what some exponential equations look like. So we have, in all cases, we have that the variable is up in the exponent. So that's part of the reason why we call these exponential equations. So rather than having like 2 times x, this would be a linear equation. Instead of having 2 times x equals 16, we have like something similar to 2 raised to the x equals 16, and we're trying to figure out what x makes this true. In certain cases, you can perform this technique. So this is only in certain cases though. We're going to see a more general approach in a second. In certain cases though, you can simply solve without the use of what's called a logarithm. So in a second, we're going to see how to solve these equations using a logarithm. But in certain special cases, you can rewrite each side using the same base. So I'm looking at this. We've used this before, actually, on page 126, example 5. But just as a reminder, if we have 5 raised to the 3x minus 6, and if we have this set equal to 125, well, 125, luckily, is the same as 5 cubed. Just show you that here. So 5 cubed, there's that 125. So 125 is literally the same as 5 cubed. So once we have the bases the same, so notice we have a 5 and a 5, all I'll need to do now is to set the powers equal. So 3x minus 6 needs to be equal to 3, or else we're not going to have equality. So add 6. So 3x equals 9, divide by 3. So x would equal 3. The problem though is, what if we had a similar but different problem? What if we had 5 to the 3x minus 6 equals 126, right? So if we had that situation, we would no longer be able to do this 5 to the third thing, right? And this whole process breaks down. As soon as we have a number that is not a power of 5, then we cannot set the powers equal because we can't make the bases equal, right? So we need a more general approach for that reason. And that's where a logarithm comes into play. So many exponential equations cannot be written as powers of the same base. So for those general cases, we use what's called a logarithm to solve. So I'll show you these first couple. Here's a kind of an outline of what you could do to solve these. Notice we have this problem. It's no longer 125 over here, it's 134. So I cannot write 134 as a power on 5, at least not very easily. So here's what you do. You choose a logarithm. So what I'm going to do is attach a logarithm to both sides. So log, and then what I'll do is I'll choose a base that's the same as the base that we had. So every logarithm has a base. And I'm going to choose a base 5 logarithm. And I'm going to apply that to the left. And then what you do to one side, you have to do that same thing to the other side. Okay. So what ends up happening is, let me show you a couple things. So you may have this button on your calculator, this button right here. So this button here. Press that button. Press, let's use a 5. And then what happens if you press like 5 squared inside of that? Press equals, you get a 2. Go back, what if you change 5 squared to 5 to the 6th? You get a 6. What if I change 5 to the 6th to 5 to the 10.1? You get 10.1. Right? So there's a property that's going on. Let me write that property here. So if you have log base b of b to the whatever, then that's equal to the whatever. And that's our important logarithm property. And that is really what allows us to solve a lot of exponential equations. So when I have log base 5 of 5 to the x, these actually completely cancel out. And what I'm left with is x, that's the only thing left over here, just the x, equals log base 5 of 134. You can check these. So I'm claiming that 5 to this number equals 134. So 5 raised to the log base 5 of 134. Right, so maybe I'll show you that a little more slowly. We have 5 raised to the log base 5 of 134. This should be 134. So yeah, this number does work. Let's try another one. So here we have 10 to the x equals 8,000. So what I'll do is I'll identify the base that the exponential is using, and I'll use that same base in my logarithm. So I'll say log base 10 of 10 to the x equals log base 10 of 8,000. Cancel because of that property. And we have that x equals log base 10 of 8,000. And it turns out that that's completely the same as, so you could write this as x equals log of 8,000. So if you don't write the base and it says log and the base is not written, then that's assumed to be base 10. Okay, base 10 comes up so often that we have this common logarithm. So these are both exactly the same. Let's try one down here. So it says solve, find the solution set, then use a calculator to obtain a decimal approximation to 2 decimal places for the solution. So what was going on a couple times up here is our exponential piece, which is right there, for example, and right here, for example. Those exponential pieces were already isolated. So that's actually step 1, is you want to isolate the exponential equation. Okay, so in these first couple, it was already done, actually. On this one, we want to get this piece alone. So what I'm going to do first is to add 5. So we get 7e to the 2x equals 63. Then I'll divide by 7. So we now have e to the 2x equals 9. So now here's my exponential. So what I'll do is I'll use a log base e. Remember, this is our special number e. It's not an unknown. So I'm going to use log base e and apply that to both sides. So 2x equals log base e of 9. Right, the 2x is the only thing that survives there. Right, just like we had log base 10 cancel with the 10 to the x, this log base e cancels with the e to the 2x, and the only thing that's left is the 2x. And the only thing left to do now is to divide by 2. So x would equal 1/2, I'll just write the 1/2 out front, of log base e of 9. There's another way that you could potentially write that. So you could say x equals 1/2 ln of 9. So log base e, just like log base 10 has a special name and we can just write log instead of log base 10, log base e has a special name and you can just write ln, the natural logarithm, instead. Okay, so that is solving exponential equations using logarithms. But what about solving logarithmic equations? So let's get into that. Here's a couple examples of what logarithmic equations look like. They are equations that involve a logarithm. So here's our logarithmic equation. We have a log base 2 of x minus 4 equals 3. So in a similar way, but kind of in an opposite fashion, we're going to apply an exponential to the logarithm equation, right? We had just been applying a logarithm to an exponential equation, and now we're going to do kind of the opposite. So what I recommend is first isolate the logarithm, and our logarithm is isolated in this first case. It's right here. Identify the base that that logarithm is using, and then use that base as an exponential base. So here's what I mean. I'm going to write 2 to the log base 2 of x minus 4 equals 2 cubed. So I'm now using both sides as powers. Okay, so I identified that they have a 2 as their base, and now I'm making basically both sides of the equation powers of this new exponential equation. There's another property that's kind of the same but opposite, right? I was before going log base 5 of 5 squared, and I would get a 2. Log base 5 of 5 cubed, and I get a 3, this property. Right, we were using this one that says if you have log base b of b to the x, that you just have x. There's another one that says if you have b raised to the log base b of x, that you also just have x. And that's the one we're going to use here. So if I have, imagine 5 raised to the log base 5 of, I don't know, my favorite number, then that is 13. Right, whatever number I put here, as long as these bases are the same, just this number is going to survive. So if it's an 8, I just have 8. So that's this property in a nutshell. So over here, these cancel. And what we're left with is just x minus 4, right? What was ever inside of the logarithm is what survives. So x minus 4 equals 8. And now add over 4. x equals 12 apparently, and what I'll do is I'll check that real quick. So log base 2 of 12 minus 4, right? I'm plugging in 12 in for x, hoping I get a 3 out of this, and I do. Okay, let's try another one. So as I was saying before, we need to isolate the logarithm. This logarithm is not isolated yet. So what I'll do first is divide by 4. So I have ln of 3 times x equals 2. As I was saying before on a different page, when you have log base e of x, that's the exact same as ln of x. So this equation here is the same as log base e of 3x equals 2. So it's a base e that we're working with. So I will go ahead and write e to the left-hand side equals e raised to the right-hand side. Right, so I basically make both sides of the equation powers on the base that was involved in the original equation. And then you can apply that property up here, this one, and say, okay, these actually cancel. The only thing that would be left would be the 3 times x, and then I still have e squared on the right. You don't need to approximate e squared here. So divide by 3. So x equals e squared over 3. I'm just remembering now, I don't think I approximated this one over here. So let's go ahead and do that. It said approximate after you find the exact solution. So I'll go ahead and type in 1/2 times log base e. So log, and then to get to e, I go alpha times 10 to the x. And then I'll type in a 9. And see what this is. It said 2 decimal places. So this 8 bumps up that 9 to a 10. So I'm going to have 1.10. So I'll just write it here. All right, almost forgot about that. Okay, let's try one more. So email volume, it says the sender-based security network ranks email volume using a logarithmic scale. The magnitude m of a network's daily email volume is given by this equation, m equals log, and this must be a log base 10, of v over 1.34, where v is the number of email messages sent each day. How many email messages are sent each day? By a network that has a magnitude of 7.5. So this 7.5 is what goes in for m. And now we need to solve this logarithmic equation for v. So keep in mind, if it's not written and it says log, then it's assumed to be a base 10. So what I'll do is write 10 to the 7.5 equals 10 raised to the log of v over 1.34. Because it's a log base 10, these now cancel, and we have 10 to the 7.5 equals v over 1.34. And now I just need to multiply through by 1.34. Okay, so that's times 1.34 times 10 to the 7.5. So I'll have 1.34 times 10 to the 7.5, and this will equal V. Let's see what that is. So 1.34 times 10 raised to the 7.5. It's about this many emails. So it's about 42 million. I'll just write this number down. All right. The next couple videos will be practice exam videos. Talk to you then.